My prescription did not reach.
Okay, good morning, everyone. So how did your homework go? Any questions? Put them on chat or just say them and we get started. Now homework, I mean the problems that you guys had on my lab. Which problem did you have? Number 9, okay? The way it goes, I will do the number 9, which is from the book. And the one you have on my lab will be a slight variation of the problem I will do. So you will be able to do the problems you have. Okay, so I look at number 9, and the question is the following. They give us the following picture. Function y equal to x, the graph of y equal to x, and the graph of another one, a parabola going down. And this was y equal x squared minus 1. Okay. All right. And the question is to find the area between those two graphs. All right. So how shall we do? Let's see the idea that we developed yesterday. The idea is the following. This is the region, the shaded region. And these are my 2 points. And the idea is to take this region and divide it into a rectangle. Little rectangle. Cover the whole region with those rectangles. Find the area of each one of them and add them. And we kind of developed yesterday the formula for the area of each one. So a typical rectangle, let's draw it. That's the rectangle, the type of rectangle we will cover the whole region with. So that's my typical one. And that's SI plus 1. Okay. And we have to find the area of a typical triangle. So that's a typical triangle. So the area. Not of the whole area, the area of one typical triangle, and then we add the sum. Is equal to the length of it times the width. Let's see, what's the length of a typical triangle? The length is, and the width. Once we know that, we're actually almost done with the problem. The width of the triangle is the delta x. That's every width. Now, what is the length of this triangle? The length is from here to here. And what's the length? It's the value at the upper function. The upper function is y equal to x. So it's the value at the upper function, which is the xi. Meaning if this is xi, from here to here to xi, take away the value at the lower function, which is xi squared minus 2. So the length of the area of every triangle is going to be the upper value. That's the upper value basically, or the top value. I called it top yesterday, minus the value at the bottom curve, times the delta x, which is the width. So that's a typical triangle. Now, what's the whole area? The whole area, that's the idea now of covering this region with triangle, this whole region, and then adding the area. And this will give me a Riemann sum. So the area is almost equal of the sum of the area of the triangle, which means the sum of that. Now, almost. But the actual area is what happened. So when n goes large, what happened to the sum when n become very large? This is what happened to the sum when n, we take it out of subdivision. And when we realize that this sum is actually looks exactly like a Riemann sum. So it's going to be the definite integral x minus x squared minus 2 dx. And now there is a very important piece that I should have done at the beginning, but I didn't do it because I want you to feel why we have to do it. But the integral from where to where. Okay. All right. To know the limit, we have to ask ourselves, go back to the picture, which interval I need to divide into pieces to cover this whole region. It means I have to divide something into pieces. Which interval? According to this picture, I have to divide the interval from here to here. That's the interval I need to divide. This and this. But the question is, how can I find this point and that point? Back to you. How can I find this value and this value? Anybody? How can I find this and that? It means basically I want the x-coordinate of this point and I need the x-coordinate of this point because I need to find the interval. How can I find the x-coordinate of those points? To be able to find them, we need to find the intersection of the two curves. So once I know where the intersection, I know, you're right, David, thank you. So I need to find the intersection of the curve or where they meet. And this is crucial. Usually we do it at the first step, but I want you to know exactly why we need it. To find the intersection, how do we do? We set the y from the first curve equal the y to the second, and we solve for x. That's exactly what your classmate said. The y equal the x. Okay. Now we have to solve. How do we solve? That's quadratic. To solve it, we basically always, not basically, we always have to make it equal to 0. So this would give me x squared minus x minus 2 equal to 0. Now to solve for x, we either factor, if factoring is possible, or we use a quadratic. So this is x and x. The factor has to be 1 and 2, I think. And this is going to give me a minus 1 and a plus 2. I double check. X squared plus 2x. So it should be minus and plus. Plus 2x. I meant minus 2x plus x. That's minus x minus 2. So x equal minus 1. X equal to 2. So that's how we have to find the intersection. So in my graph, this is the minus 1 and this is the 2. So those will be the limit. So usually we do the step at the beginning. Once we have a good after this problem, because I need to know which interval I need to divide to cover the region. I have to divide the interval from -1 and 2. That would be the A and the B in my interval. So now finally I am done. So that's going to be the integral from -1 to 2 of that. And the rest is just a simple integral problem. So that's the integral from -1 to 2 of x. Now I distribute minus x squared minus plus 2 dx. And always remember that usually this piece is always the top curve. So that's really the formula if I don't ask you to do the typical triangle, I meant rectangle here. And that's the bottom curve. So finally, this is equal to antiderivative of x is a half x squared minus antiderivative of x squared 1/3 x cubed. Antiderivative of 2 is 2x. The whole thing evaluated between my -1 and 2. And the rest, I keep it up to you. Okay. Questions before I take up another question from you guys? So the steps are very clear. Step 1, we need basically to find always the intersection point to know which interval I need to divide into pieces. Step 2, okay, we say, okay, the idea is to cover this with rectangle. We draw a typical rectangle and we concentrate on the area of this typical rectangle. The third idea, we have to add all those areas. Adding them will give me a Riemann sum. And then we use the definition of the definite integral to set up our own integral. Questions, please? All right. Now, when you ask me problem, like I see number 4 and 8, you have to give me the one in the book that correspond to it. I don't know what 4 is from the book. All right. Number 9 is finding the area under 3 curve on the one stay homo. That's what I am saying. You have to tell me which one in the book. So when you guys said number 9, I picked up number 9 from the book. You have to tell me which problem in the book correspond to number 9 on the homework. Am I making myself clear? Alan?
Yes.
Did I make myself clear? No, I don't think so. When you tell me number 9, you have to tell me which number 9 in your homework correspond with which problem in the book. Can you say that from my lab or not?
It basically says find the area of the shaded region below in the figure, and there's 3 curves.
Yeah, I understand that, but do you know which problem from the book? It corresponds to which problem? Is it written on your homework? Like
no, it says only question 9. It's 6.2.63.
Okay, so it's number 63 in the book.
Yeah.
Let's do it. So I would rather you write number 63 because I didn't memorize the corresponding numbers.
Okay.
You with me now?
Yeah.
Okay. All right. Now I have other question. Number 4 and 8. I will take up. So Sagam, you asked me 4 and 8. Do you know which one in the book? But that's the way.
Actually, yeah, I don't know, but I can send the picture of the questions to you on email.
I want you to get. Go ahead.
Because I don't know how should I match the book questions and the homework questions.
Okay, so we have to get used to that because it's hard for me to do it otherwise. Okay, I know that it's the first day. We have to get used to that. Right, so you have, like Alan did, I think on the top of the homework, of the top of my lab, it's written which problem from the book it is.
Okay, I will check it out. Mm-hmm.
Okay, all right. So I'm gonna pick a problem and all the problems are basically the same. So I'm gonna put number 43. I hope it's one of those you're asking because they are fairly similar. And then I will look at 63, the one Alan asked. I'll give you a hint, but I will not do it. I want you to think about it again. So I look at number 43, whatever this is. Find the area of the region. bounded by y equal to x, y equal 1 over x, y equal to 0, and x equal to 2. Okay? All right, so this time we don't have the graph. So step number 1 is going to be sketch the graph. So I will start by sketching the graph. The region is bounded by y equal to x. Y equal to x is this region. Y equal 1 over x. 1 over x is this curve right here. Y equal to 0. Y equal to 0 is the x-axis. X equal 2. This is 2. X equal to 2. But before I jump any further, the question is x equal to 2. Is it here or here? To be able to, it means, is it before the intersection or after it? So because I need a very good graph to be able to do those functions. All right, I cannot know that till I know the intersection point. So I have a good picture. So let me find the intersection first. So intersection point. Otherwise, I don't know where to put my 2 actually, okay? All right, so intersection. I have to set x equal 1 over x, the y from this function equal to the y from that function, and solve for x. Okay. To solve x equal 1 over x, the best way to do it is actually cross multiply. I get x squared equal to 1. It means x equal plus or minus 1. Okay, so this is going to give me, so this point is 1, 1. Okay. All right, so this is the region I am interested in. Okay, so the region between y equal to x, y equal 1 minus 1 over x, y equal to 0, which is the x-axis, and the line x equal to 2. All right, so I'm going to find this area. You guys have to help me out. So it's a little bit different than before. And let us watch what's really happening in this region. When I take my typical triangle, rectangle, if I take it before the point 1, the top curve is the line y equal to x. So the formula here is going to be the top curve, which is x minus 0, because the bottom curve is 0. However, if I take my rectangle here, the top curve is y equal 1 over x. So there is not one formula for the typical rectangle in this picture. So how I'm going to solve this problem? Let us note that the top curve changing. So how I'm going to solve this problem? Any ideas?
Could you split it into 2 parts?
We have to split it into 2 parts. We have no other choice. Okay, my top curve is changing, so I have to split into 2 parts. So this is the kind of problem we're going to encounter a lot. So I have to split it right here. I will call this R1, and I call this R2. And then let me analyze. If x between 1 and 2, between 0 and 1, right here, the top curve is x. So in this region, the top curve is f, and the bottom curve is nothing more than the line y equal to 0. If x is between 1 and 2, the top curve become 1 over x. And the bottom curve is the line y equal to 0. So to find the area of this region, I have to split my problem. And in this problem, I'm not going to do typical rectangle. I'm going to jump immediately to the area of the region. It's going to be equal to the area of R1 plus the area of R2. Now let's see what the area of R1 is. The area of the first region, we have to divide the integral from 0 to 1. So this gives me the boundary. The top curve here is y equal to x. And the bottom curve is 0. That's the first one. So I had to divide here because of what's really going on. Plus the integral. R2 is from 1 to 2 of my top curve, which is 1 over x. The bottom curve is actually not important here, which is 1 over x dx. And finally, it's going to be equal to a half x squared between 0 and 1 plus ln of x between 1 and 2. And the rest you guys finish. So it's going to give me a half plus ln of 2 minus ln of 1, which is equal to 0. So this will leave me with a half plus ln of 2. Okay. All right, any other questions? Okay, I'm gonna give you a hint for number 63. And tomorrow you can ask more of your questions. Okay, so we can do something else. So I'm gonna give you a hint for number 3. Listen very carefully. And if you guys struggle with it, I will do it again. For sure, I'll do it again. But I have to give you a hint. So I will not do the whole problem. So this is number 63. I have a line. According to the book, y equal 8x. I have another line. Y equal 5 over 2x. And I have a curve. This curve. And this is y equal 9 minus x squared. Right? And the problem is I need to find the area in between. This area. All right. Exactly. If I need to find this area, I really have a problem. Let's see what the problem is. It's exactly the problem I had a minute ago. First, I need to find all those intersection points. And those intersection points are not hard to find. For this one, you set y equal 8x equal y equal 9 minus x squared. And for this intersection point, you set y equal 5 half x equal 9 minus x squared. And you find the two intersections. But now look what the problem is going on. Once I find the intersection, and let's see, I cannot visualize it. So once we find the intersection point, you guys will do it and look what the problem is. If I am this side, my top curve is y equal 8x. My bottom is 5x. If I take my rectangle here, if I am here, the top curve is y equal 9 minus x squared. The bottom curve is y equal 8x. So the only way to do this problem is to divide it into two regions, R1 and R2. You have to find the area of R1 by itself, and then you have to find the area of R2, and then you add both areas. Okay, so it's going to take a little bit of time. Step number 1, you have to find the intersection point. Can anybody, x equal to 8? Actually, x equal to 1. Because if x equal to 1, this is give me 8. And this curve gives me 9 minus 1, which is 8. So this is actually the intersection point right there. So here you have to figure out if x is between 0 and 1, your top curve is 8x. That's the top curve. The bottom curve is y equal 5/2x. So that's one situation. And then for x between 1 and whatever you find here, let me call it b, because it's up to you to do it. My top curve is this one. It's going to be 9 minus x squared, and my bottom curve is going to be 5/2x. So this is in mind. You set up 2 integral and then you add. Questions? Okay. All right, so for tomorrow, you guys have a better idea now how to finish your homework. So I want you all to finish, and I will be watching you through the night, see how well you guys are doing. Okay, so tomorrow you have the right to ask me more questions, just simply because the material is a little bit new for you. Okay, and I will go over them. Right. Today, we're definitely going to stay along the same line. We're not changing, but with a little bit of a twist. So I'm going to take a problem fairly similar to what we did, fairly similar, and I will ask you the following question. So my problem is, and please, I'm going to ask, I need your help here. I'm going to take the following region. So let R be the region bounded by the graph of y equal x minus 2 and x, be very careful here, x equal y squared. All right, so there R is the region bounded by y equal x minus 2 and x equal 5. So find the area. Step number 1, regardless what the problem is, I need to sketch. All right, let me sketch here. Okay. Y equal x minus 2. That's nothing more than a line. The intercept is at minus 2, so it's a line starting from here and go all the way like that. So that's y equal x minus 2. Okay, now x equal y squared. Watch carefully here. X is equal to y squared. How's the graph of x equal y squared? Anybody knows? Remember, x is y squared, not y equal x squared. Be very careful here. Let us remember, if x equal y squared, it means y is plus or minus the square root. Means we have 1y, which is the positive square root, and 1y equal minus the square root. Right, so let's sketch that. Y equals the square root of x. So that's y equals square root of x. And y equal minus the square root, right? It's a horizontal parabola. Exactly. I want you guys to scream and tell me that. And y equal minus the square root, which is down here. So it's like a parabola, but toward the x-axis. All right? So that's y equal minus the square root of x. And this one goes like this. Sarah, I want to find the area. Quickly, what do I need to do? I want please answer very fast. How can I find this area? I want you to analyze it for me. One guidelines usually is that to find the area, when I take those rectangles, to be able to really find them, I need to say what's my top curve and what's my bottom curve, to be able really to find the length. What's really happening here? What's the bottom curve in this problem?
X minus 2,
It's -2. What's the top curve? Please, all of you.
square root x.
Is it okay? What if my rectangle is here? What's the top curve?
Would be plus minus square root x.
The top curve is the square root of x. What about the bottom? Minus the square root of x, right? The top is the square root minus the square root. If I take my rectangle here, my rectangle here, the top is the root x, but the bottom is x minus 2. So here, the bottom curve is actually changing. Between this point and that point, the bottom curve is changing. It's changing right there. That's the change. So from here to here, the top curve root x, the bottom minus root x. From here to here, top curve is root, bottom is x minus 2. So how can I solve this problem? Now the intersection point, just to make our life easier, I just find the intersection point for you. That's 1 minus 1. And this intersection point is 4, 2. Don't worry about those. So how can I find the area of this region? It's a little bit problematic because my bottom is changing throughout the region. Okay, so the way we're going to do that is quickly, what's the keyword? Let me ask one of you. I want to do call V. Are you with me?
Yeah, I'm here.
Okay, how do you think I'm going to do it?
Splitting them.
Splitting them. All right, help me in the splitting. How I'm going to split? Go ahead, call quickly.
So for R1, you're going to split it at where the intersection is.
Okay, so X is between where and where?
First one is going to be the negative square root. Right.
So the top one is going to be what? For R1. This is R1. What's going to be the top curve? Look at the graph.
So the top curve,
Yeah.
the square root x.
Well, the bottom curve.
Negative square root of x.
Very good. And this holds for which value of X? Quickly call. You're on the right track. Which interval I have to divide to cover the region R1? Anybody can pitch in quickly?
0 to 1.
0 to 1. Does make sense, Cole? From 0 to 1?
Yeah.
From here to here. Okay, this is the one. That's the one. That's the one, the intersection. Okay, now finish the problem for R2.
R2, let's see. Which one, where do you want me to start? With the y's or the x?
You mean the top or the bottom?
Yeah.
Okay, what's the top?
Top is going to be the square root of x.
What's the bottom?
X minus y.
X minus 2.
R2, yeah.
Yeah. Where is the X? Go from where to where? I mean, which interval I have to split to cover this whole region?
I think it's what, 1 to 4, I think.
1 to 4. Absolutely correct. That's the 4. The 4 is this one.
Yep.
Intersection. That's my 4. All right. Why did we have to split? Because in this problem, the bottom is actually changing across the area. So to cover this whole region, my typical rectangle is changing. The formula for it is changing. So I have to split into 2 pieces because my bottom curve is changing. So now the setup, the problem is very easy now. So the area of R is area of R1 plus area of R2. Okay, so what's gonna give me? The first one is the integral from 0 to 1 of my top curve minus my bottom curve. Don't be afraid of having minus the square root of x, because that's correct. Plus the integral from 1 to 4 of this time, that's my top curve. My bottom is x minus 2. And then you do both integral, you evaluate, and you are done with the problem. All right. So this problem we had to split. And the reason we had to split is actually because my bottom curve is changing. I don't have a unique bottom curve, so I don't have one formula for the typical triangles. So we have two different formula. It depends on the region. So we had to split. Now, sometimes, not all the time, we can get around splitting. And we can evaluate this as only one integral. Right? So the question is, how can we do that? Should we know how? Absolutely. X equal y squared, we should know how to do it. Absolutely. Okay, you should know without a calculator. You know, it's so basic. All right? Yeah, absolutely. It's very simple. I will not ask you to graph hard stuff, but something like x equal y squared, you should know it. All right, so what we're going to see today is how can I avoid this? And let me tell you what the idea before I got into it. The idea is going to be, instead of covering this with those vertical rectangle, we're going to start developing the idea of covering with horizontal rectangle. So instead of doing things with respect to x, we're going to do them with respect to y. So before I get into this and explain it, I need two simple comments to be able to develop the idea of horizontal rectangle. Comment like this. So two notes first. So the idea is how to go around splitting. But before we need the following notes. All right. I'm going to ask you a simple question. Suppose I have, this is my horizontal axis. That's the line. This is my 0. And let me call this E, and let me call this F. Right? My question is, what's the length of this segment?
F minus E.
F minus E. That's the right value, if you want, minus the left value. So the length is F minus E. F, you take away E. So the right value minus the left value. And some of you know where I'm heading. Question number 2. Suppose 0 is in the middle. My E here and my F here. What's the length of this from here to here? Does it really matter if 0 is in between them? Because here the geometry is easy. What is the length here?
Minus E again,
F minus E again. Why?
because E is negative, so
Right.
when we put minus, it becomes positive.
Because this is F. You agree with me? It's positive. That's the length. The length from here to here, the length is not E, because E is negative. This length is actually minus E, because if this is minus 2, it's going to be minus 2. So the length is going to be F plus minus E. It means F minus E. So the distance, if you have 2 points on the horizontal line, regardless where they are located, the distance between them is the value, the right value minus the left value. And we did something like that when we took point on the vertical line. So that's the first note I need. So always the right value minus the left value. The second note I need is the following, and that's the important one. Suppose I give you the graph of y equal x squared. Okay, something that you've seen since in middle school. Here, I'm giving you y is a function of x. What do I mean y is a function of x? Means, and we graph it, y equal x squared, we graph it. Okay. In this situation, if I know x, this formula basically is giving you the y. So if I graph this, and I tell you this is 4, x equal to 4, this formula will give you the y that correspond to x equal to 4. It means if I go back and I hit the graph, if this is 4, the y gives you this vertical distance. This is 4, so this is going to be 60. Okay, so if I pick any point here, I call it xr, that's something you know, then the formula will give you the y. It means if this is xi, the formula is giving you the y. It means the y is the xy squared. It means this vertical distance is xi squared. So this is when y is given to you as a function of x. Now, in this course, sometimes instead of having y as a function of x, we're going to be giving you x as a function of y. So I'm going to change the x's and the y. So I can tell you, suppose x equal y squared. So x equal y squared, it means here in this problem, if I know y, sorry. So here, x is a function of y. Okay, so things are changing a little bit. And the graph of that is basically, again, it's the same thing as a parabola, but is what your classmate called a horizontal parabola. But what does this mean? Now I'm going to ask you the function. So here, if I know y, the formula giving you the x. So suppose I take the point here. That's 4. My question to you is, so here 4 is that. What's the coordinate here? Back to you. Exactly. This is my 16. It means this formula, I know the y, it gives me the x. So what does the 16 represent? It's the vertical distance from here to here. So the formula is giving you the vertical distance, not the horizontal distance anymore. All right. So in a more abstract way, if I tell you this is yi, and I take this vertical line, sorry, this horizontal line till I hit the curve. Right now, I have the yi. So what is this coordinate quickly? Exactly. It means from here to here, I have the yi squared. All right. So that's really the idea. So starting today, sometimes the function, instead of giving you y as a function of x, why not giving you x as a function of y? In those problems, you have the y. You have to figure out the x. The formula gives you the x. And the x represents this horizontal distance. That's really what the x represents. All right. So now I'm going to change a little bit the setting of our problems. And this is the problems we're going to be dealing with. So idea is area. So I'm going to area between two curves using horizontal slices or integration with respect to y. Okay, so let's see what my problem is. So now I'm going to take a region. So let S be the region. Bounded, and see how my language is going to change a little bit now. From the right, it's not up and down, by the graph of x equal f of y. So now x is a function from y. The left by x equal g of y, and the lines y equal to c and y equal to d. So very different look at my graph. So I will draw the graph here. Okay. It's bounded from the right by x equal f of y. So that's x equal f of y. That's the right boundary. The left by x equal g of y. So this is x equal f of y. Okay. The right x equal g of y. They don't have to be the same, but for the ease of the picture. So this is x equal to, that's the g of y. So both graph, x is a function of y. The lines x, y equal to c. This is c right here. And I have the line y equal to c. That's the line y equal to c. That's the line here. And d is right there. And this is my region. Okay. And the question is, we have to find the area. Find area of S. Right. So how are we going to find the area? Right. This problem, we are going to repeat the same thing we did in the previous situation, but the question is, instead of splitting this region horizontally, vertically, which is almost impossible here because the curve, the rectangle, the upper curve, lower curve is really not under our control. We're going to split it actually horizontally. It means we will take the interval CD, the interval on the y-axis. So what I did for the x-axis, I'm going to do it for the y this time. I'm going to divide this into pieces, okay, etc. So we're going to divide the interval CD into pieces and cover the region with horizontal slices or horizontal rectangles. So my first rectangle is going to be like that. Okay, my second rectangle, my third, that's really the idea. And every piece from here to here, this is, I'm going to call this delta y. So that's what I'm going to do. So I'm going to do the same thing, but changing the cover and so on and so forth. So that's really what I'm going to do. And then I'm going to find the area of each one of them and then add the area. That's what we do technique. So we divide CD now. CD, the interval CD into subinterval. And we call delta y, not very carefully, it's not a delta x anymore, the length of each one. So delta y is going to be from here to here, it's d minus c over n. Right? And now I need to find the area of every rectangle and add them to each other. And this is going to be my y0, this is my y1, this is yi, and this here, yi plus 1, and so on and so forth. So to do that, I will take a typical rectangle, find its area, and then sum up. So typical rectangle, because the picture for one rectangle will be easy, for all of them will be hard. So I have this region right there, this region. This is my D here. And this is my C. This is Y0, and this is Yn. And I'm going to emphasize one rectangle and find its area. This is Yi, and this is Yi plus 1. And this is my rectangle right here. This is the rectangles I'm going to use to cover. Okay. This here is x equal f of y. And right here is g of y function. And my question is, what's the area of this piece? Okay, so that's typical rectangle. All right, if we find the area of this, we're done. Then the rest will be easy. So you have to help me out a little bit. To find the area of a typical rectangle, let me find what's the length of a typical rectangle. And what's the width? Equal. All right. The width is from here to here. Okay, quickly, what's the width? Because I will take two extra minutes from you guys. What's the width? How much do we have from here to here? Delta 1. That's the width. Now the hard part, what's the length? How much will I have from here to here? Watch the picture very carefully. This is yi, right? What's this point right there here? This is yi. This point is on the graph of this function. So if this is yi here, this point here, this is the yi, this is going to be f of yi. Means this point here, that's f of yi. That's the right point. If this is yi, the point here is going to be, that's the yi. This point is on this graph. That's the g of the yi. So this point here will be the g of yi. So what's going to be the length? That's f of yi from here to here. You're going to take away g of yi. That's the g of yi. So it's f of yi, because that's the graph, minus the g of yi. So the length is going to be the value at yi of the right function minus the value of yi at the left function. So the length is going to be the value of yi of the right function minus the left function. So the area of a typical rectangle is going to be the length times the width. The width is delta y. The length is f of yi minus g of yi, because it's from here to here, you take away from here to here. That's a typical rectangle. Now, finally, what's the area of the region? And then we stop. Okay, what's the area of the region? So I emphasize a little piece, and then I generalize. So the area of S is it's almost equal to the sum. It's the delta y. Watch carefully, everything is delta y. Everything is in terms of y this time, not in terms of x. So I'm totally switching scenario. So that's the area. Now this is a Riemann sum. It's a Riemann sum in y, not in x. So the area of S is going to become the following. I'm going to rewrite this as a definite integral. F of y. I'm going to turn this Riemann sum into an integral. Minus g of y. The delta y is the dy. And finally, the limit. What are the limits? I go back to my picture. I said, which interval I need to divide into pieces to cover my whole integral. I need to divide the interval on the y-axis from C to D. So basically, we're reversing our way of thinking. Everything we did before was the y, was the x, we're doing it for the y. And that would be the area of S. This should always is the right curve, and this is all the left curve. Okay. All right, I have to stop here because I was hoping to give you one example. For tomorrow, I want you to go again over the problem I've assigned for today, and I hope that all of you will be able to do them completely for tomorrow. And I will not assign you homework. Tomorrow, I will work on this a lot. Okay. All right, if you have any questions, please, the class is dismissed. Stay with me. And bye for now.
Professor,
Yes. I'm listening.
trying to